Hi, I'm Gerald Foster, president of Sunnybrook Welding. About 20 years ago, we got into the development of the fundamental chemistry of thermochemical boronizing. And most people, when you begin discussing the subject, mistake it as an alloy, mistake it as something other than what it is. What boronizing is a reaction to the iron on the surface of a part. We take boron and we free it up with an activator, and we react it with the iron, and what we want to form is a layer of iron boride, or Fe2B, on the surface. Now if you do it too hot or too fast, you produce FeB, and they call that the high grade layer, but the high grade layer won't stick to the metal below it. So back in about 2000, we had a story put in the Western Producer, the farming magazine, about it, and it showed the benefits of it. And we've done many tests, and we've gone with the original equipment manufacturers in the field to test this product. And what we found is we never get beat. Iron boride will outperform for wear, hard chrome, any of the alloys, any heat treatment process. But the problem with it is it's very difficult to manage as a process, because you can't weld it, you can't fabricate once it's done. So it has to be done to a completed part, or you have to get very clever in masking it off. So we decided then that we needed to reconfigure how we build concaves so that we could boronize these modules. Boronizing not only produces an extremely wear-resistant surface, it also has a severely reduced coefficient of friction. So we knew if we could ever produce the belly of a combine with a layer of iron boride, we'd reduce the input shaft power required to turn the rotor. Now, if you look at the picture of the cross-section of the layer, you'll see the homogeneous iron boride zone. And that drops in time, temperature, it reacts in, and you see below it, you see the pools, the dark shaded pools of carbon. That tells me that this cross-section is an annealed substrate. It hasn't been hardened below there, because the carbon has all come together and puddled or pooled. Now, the one benefit of boronizing is the carbon doesn't disappear. What happens is, as you boronize and you form that iron boride layer, the carbon is pushed in front of it. So what you end up with is a layer of iron boride 3, 4, 5,000 of an inch thick, and as well another 10 to 12 thousandths of an inch where the carbon that was on the surface layer gets driven in front of the reaction. So you have a carbon enrichment zone. So if you were to heat treat this product subsequently, you'd produce a very hard layer underneath the iron boride layer as well. So we'll take a look at some samples here, field samples. These were done in Oregon. You can see quite a significant difference between the wear between the iron boride treated parts, or the boronized parts, and the control. That control piece had failed in one season. So what they're looking at there is a possibility of getting 3 seasons on a part versus 1. And you look and see now we're doing on these gray parts, you see that we're doing these same modules for conventional combines as well. What we're trying to do, or what we were successful to do with the boronizing process, was get rid of chroming. Chroming was a nuisance, not only in finding people that were able to do the process for us on a timely basis, where we sit in the oil and gas industry here, but chroming is a bad process for the environment. So the sooner we could do away with chroming, the better off we knew we'd be. And boronizing is a very environmentally acceptable alternative to chroming. So we see it as having a huge future in the production of combine parts.